Okay, we're here to talk about chapter 11.2, geometric series. So geometric series are built on the geometric sequence. So for instance, geometric sequence with r equals 1/2, basically just raise higher and higher powers of that and add, list them all out for the sequence. But for the series, we list them out and add them up. So the first term is 1/2 for n equals 2. The second term is 1/2 squared, and so on. So geometric series that we define like this has two building blocks to it. So whatever your first term is, so in this case a is equal to 1/2, and like whatever the common ratio of r is to cause us to move from one term to the next. Okay, so in this case, every time we have to multiply by 1/2 to get from one term to the next. So we have r equals 1/2 in this example. This example has both of them equal. That doesn't have to happen. You can start off, obviously, with any number here for a and get the same sort of behavior, okay? Now, geometric series are important. They're going to also be the last type of series that we can sum by finding a formula for the partial sums. We'll be able to sum more series when we start talking about power series. And actually, it also turns out that the geometric series will help us build some types of power series as well. But this is going to be the last one that we can actually find the sum of by using the partial sums. So let's take a look at how we can do that. It's not as straightforward as the telescoping series, but it is a nice demonstration, pretty easy. So by definition, the sum of a series is the limit of the partial sums. A series is not a sum, a series is a limit, even though we call it a sum. So it's a limit of this thing. What I've listed out right here is the kth partial sum. This first term right here would be what we get by plugging in n equals 1 into my formula. Excuse me, n equals 0 into my formula. This term would be what we get by plugging in n equals 1, this one by n equals 2, and so on. This would be n equals, oh, I'm actually off by 1 here. What did I do? Okay. This is actually a good time to talk about this. This series here, as with all series, has many different ways of being expressed. So I'll put right here that we can change the series. I'll let you to fill it in while I'm speaking here. This formula that I've written here is identical to this formula that starts at the different index of n equals 1. So if you think back to chapter 11.1, the exercise of finding formula for a sequence, you can find different formulas depending on what index you want to start on. So this one, if I start on n equals 1, then I need to subtract 1 to get back to this formula. I could also start on whatever I want, n equals 7, how about? And that would be this one. Okay, so this, the way I've written things out here is actually for this series here that begins at 1. So let me fix that. This would be for n equals 1, 2, 3, so on. N equals k for the last one. It is the kth partial sum, however, so it makes sense that we've added up k things. So we need to find a formula for this. But obviously, there's nothing here that's going to cancel out like happens for telescoping series. So instead, we're going to be a little bit more clever about it and notice a pattern that happens, the obvious pattern. If you multiply by an r, you get from one term to the next. So what that actually means is to take this partial sum and get from one partial sum to the next, I just need to have one more term here. And a times r to the k would be my next term if I had added one more term. So let's, instead of adding that new term, let's multiply by an r and try and make it. So let's take this guy. Notice that if I multiply it by r, there's r in front, this term gets multiplied by r, this term gets multiplied by r, gets multiplied by r, everything gets multiplied by r, and sort of moves up by 1 in its power, okay? So we'll say multiply by r here. So the only thing that's missing here to make this actually the next partial sum is the first term a here. So it should be clear that if we take the difference between these two, we'll get a lot of cancellation, and we'll just be left with two things that do not cancel out, a and this last term here. So here's what I get if I subtract the second line from the first. Subtract the second line from the first. Okay. And you can see all these middle terms canceled out, and we're left with this one and negative copy of this one. Okay. So this is actually a formula that we can use to solve for our unknown. We want to know what SK is, right? Here's a formula involving SK, so let's solve for it. So we need to get SK alone on one side of the equation, so standard practice. Collect like terms. In this case, it means adding these two terms together to get a total of 1 minus r copies of SK. Then we divide by that coefficient in order to isolate the SK. Although we should be careful that we can't do this division if we were actually dividing by 0, right? That's undefined. So this step from here to here only works for r not equal to 1. If r is actually equal to 1, so let's go ahead and supplement this with what happens if r equals 1. It's actually very simple, right? Just come back up here. What is SK when r is equal to 1? Well, this would be a, this would be a times 1, this would be a times 1. Oh, they're all a's. How many a's do we have? 1, 2, 3, 4, 5, 6, 7, k of them. So if r is equal to 1, then SK is equal to KA, K copies of A. So this is actually very simple. It's even easier for the case that we left out there. And we can take the limit now. What happens to this formula as K goes to infinity? Because this is the formula for the partial sum, and to find the sum of the geometric series, we need to find its limit. So here we go. Here's our guy right here that I've mixed up again. Let's go ahead and write it in our form. There we go. I can leave this one like that because after all, I said that they're the same thing. But this one does need to be fixed to make sure that this partial sum agrees with this formula here. And there's the formula I found for SK right there. And SK is, of course, this partial sum here. And in the limit, we need to think about what the geometric series is doing. What's this term doing as K goes to infinity? Because everything else is fixed. So it's just really this kth power here. If R is positive, then it blows up, right? So that's what happens here. If R is negative, then it blows up and oscillates, so it's still divergent. If R is equal to 1, then we're over here actually. And so we would end up with the sum from n equals 0 to infinity being equal to, of AR to the n being equal to the limit as k goes to infinity of KA. And of course, this would blow up. So divergent, unless, of course, A is equal to 0, but it's not going to happen. I mean, no one's going to look at a geometric series which is 0 plus 0 plus 0 plus 0 and think this is a geometric series that needs to be evaluated this way. So really all of this operates under the hypothesis that A is not equal to 0. So that's what happens if R is equal to 1. What if R is equal to minus 1? Well, then this term is oscillating again, and we still have divergent because it's just going to be plus A minus A, plus A minus A, plus A minus A going on right there. So it'll never serve it down to a limit. And finally, that leaves us with what happens if R is less than 1, or I should say, if the absolute value of R is less than 1, or that R is smaller than 1, to let the word smaller mean closer to 0. And this limit then becomes, well, this term goes to 0. And so we're left with A over 1 minus R. Okay, so like I said, this is the last series that we're going to be able to sum by actually finding a formula for the partial sums. And it won't be until power series that we can find another way to get around that problem. Basically, the problem is that finding formulas for partial sums is difficult. This formula right here, this is not a closed form formula. What that means is that the formula itself actually changes as the value of k changes, right? As the value of k changes, we've got to use these ellipses. That's probably the best indicator that you don't have a closed form formula, is that you're using ellipses. This one, however, is. Okay, this is a closed form formula. And that's what we want to be able to evaluate these sums. Closed form formulas. Okay, so next let's take a look at using this formula.